Hello. In this short presentation, we're going to introduce you to the fundamentals of ultrasound body composition. Ultrasound's been around for many, many years and routinely used in medicine and has a long history of safety and accuracy. Conventional imaging ultrasound is often referred to as B-mode ultrasound. That's what gives you the images that most people are familiar with. BodyMetrix is an A-mode ultrasound device. Think of it as sending a single beam, and it gets information about tissue along that single beam. There's a large volume of literature showing that ultrasound can be effective both in measuring fat thickness and percentage of body fat. Beyond percentage of body fat, ultrasound can be used to measure muscle thickness and structure, and we'll show you that a little bit later. How does a BodyMetrix work? Well, the best way to think of it is that it's very analogous to radar and sonar. The BodyMetrix probe emits a short pulse of ultrasound which penetrates into tissue, and it reflects at key points. And typically ultrasound reflects when it sees changes in what's commonly called acoustical impedance. Now in most cases, this translates into different tissue types. So for example, if the ultrasound is going through fat and hits muscle, you'll get a reflection at the fat-muscle interface. If it's going through muscle and hits a fascia boundary somewhere in the muscle, you'll get an echo there. And similarly, you'll get an echo when the muscle reaches bone. So strong signals appear at tissue boundaries: fat muscle, muscle bone, fascia, ligaments, arteries, etc. So that's typically where you see a strong echo or strong reflection. Now, how do we convert that to a thickness measurement? Well, we know roughly the sound speed in tissue. Now, sound speed does vary a little bit from tissue type to tissue type and also from person to person, but it's pretty close. So what we do is we measure how long these echoes take to come back to the system. We know approximately the sound speed, and from that we can measure the thickness. So accounting for the variability, for example, in fat sound speed, you can get errors in thickness of maybe as much as plus or minus 3%. That's pretty small error considering all of the other sources of error that can occur. So if you use the BodyMetrix ultrasound system, then you're pretty familiar with the measurement data. There's a measurement data graph that's really a snapshot of the ultrasound signal coming back from the tissue. The y-axis is the signal amplitude. So it's an indication of echoes coming back, as I mentioned before. So high spikes, for example, the spike here about 3.8 millimeters, are indicative of tissue boundaries. In this case, the first spike is very commonly known as the fat muscle boundary. So this would indicate the yellow line here, or the yellow region indicates the fat boundary or the fat layer. Typically, if you have a bone, the last large spike is the muscle bone boundary. Ultrasound does not penetrate bone, so you see it's very characteristic of the last sound. So typically, what we would term as the muscle region would be the extent from the fat muscle boundary to the bone. And that's this region here that's lightly colored. So very simply, that's what the measurement graph is. In the past, we've done studies to compare ultrasound body composition measurements to traditional X-ray CT, etc., just again to validate it. This shows a measurement data graph of the ultrasound showing a fat layer of about 3.8 millimeters and muscle layer about 48 millimeters. It's very, very good agreement with what we saw in the X-ray CT and these figures of a bicep. Here's another example, and this is a thigh, and we get very good agreement between the two, as you would expect. Remember, you know ultrasound's been used and validated for a long, long time, so there's really no surprises here that it agrees with X-ray CT imaging. Many people are familiar with calipers, and how does the BodyMetrix compare to calipers? For caliper measurement, you'll grab the fat layer and you'll squeeze it, and then you'll measure the thickness of the calipers. Now calipers measure skin fold, but not the true fat thickness. So caliper measurements can often be about 1.5 to as much as 3 times the fat thickness measured with the BodyMetrix. So in order to calculate percentage of body fat with the BodyMetrix, we use a modified caliper formula. This is an example of a study conducted both at Pepperdine University and our own internal study done on Firemen. And this is showing how the caliper measurement compares to the BodyMetrix measurement. And again, as I mentioned before in this, for example, the chest, we've got a good agreement, close to 2S, okay? In other words, the caliper measurement was approximately twice as much as the BodyMetrix measurement, and that's on average what you would expect, okay? Now, if you look at a place like a thigh, we're seeing a little bit thicker layer, and part of the reason is that you have a really, really tight skin on the thigh. And what can happen often is that you can't pull in the fold, and you end up getting an effectively thicker layer. By contrast, if you have the abdomen where you're actually often dealing with thicker layers, it can often be hard to grab the full fold, and there the fat thickness can actually be underestimated. So that's how the two systems, Calipers and BodyMetrix, compare. Now, as I mentioned to you before, the BodyMetrix is a traditional A-mode device, so it's a normal one-dimensional mode system. So when it's used, normally the ultrasound goes down and you get this kind of measurement data showing the key spikes and reflections. Beyond tissue thickness, the BodyMetrix can be used to produce cross-sectional images. How do we do that? In this case, you actually apply a little bit of gel and along a line of tissue that you want to scan. So for example, if you're doing the thigh, then you might scan from the midpoint down to the kneecap. So you lay down a track of gel, and then what you do is simply slide the device along that track to produce a two-dimensional image. These images are produced by stitching together the one-dimensional images that you're familiar with from the measurement data. That gives you, in the end, a two-dimensional image that shows you the tissue structure along that line that you can scan very much like the animation here. Here's an example. This is a thigh scan, and the left side of this image you can think of as being a few inches above the midpoint of the thigh. And now what we've done is we applied the gel. On the thigh, I'm going from above the midpoint down towards the knee. And what we do now is we simply slide the device, the BodyMetrix, along the skin towards the knee, along the gel track, and produce a two-dimensional cross-sectional picture. In this picture, we're seeing in the white here tends to be the strong signal or strong echoes. So this first interface is the fat muscle interface. This first is about 8 millimeters of fat here. Gets a little thinner and then gets thicker as you approach the kneecap. This line down here is actually the interface between the two main muscle groups in the thigh. And the final kind of feature you see here in this white area is the muscle-bone interface. These red lines have been added kind of just for clarification. But that's the structure or cross-sectional image of a thigh. Here's another example. This shows two different thighs. Again, for these images, both of them are collected from scanning above the midpoint of the thigh down towards the knee. The individual on the left has a fat layer that's approximately 12.4 going to about 11 or even 10 millimeters, where the person on the right has a thinner layer. It's an 8.5 millimeter layer going down to as little as 5.8 and then back to 8.8. So this person has lower body fat than this individual. And again, you see the structure, and at the same time, you see this individual has a thicker muscle. The maximum muscle thickness is about 50 millimeters compared to 36.3. So one of the things you can also do with the BodyView 2D imaging is look at variations. And one of the concerns when you're making body composition measurements is exactly where do you put the device and where do you make the measurement. So it is important, and sometimes you get a feel for just how important it is. Here's a scan of a thigh over a 4-centimeter area. That's a little bit over 1.5 inches. And you're seeing that in this region along this line, that the fat is varying from about 8 millimeters down to about 6.5 millimeters as you approach and get closer to the knee. So in this case, you definitely want to position the BodyMetrix within about 1 inch from measure to measure to make sure you're consistent and you're not being fooled by the tissue variation itself. The cross-sectional imaging capability of the BodyMetrix allows us to look at other areas and do scans. One of the more important ones or more interesting ones is the waist scan. The waist subcutaneous layer of fat is actually broken down into two compartments. There's a superficial layer, or something more commonly referred to as the superficial adipose tissue layer, which is between the skin and the fascia layer. And then there's a deeper adipose tissue layer which goes from the fascia to the muscle. You can see it in this X-ray imaging, but you can also see it here in our ultrasound image. This scan at the left side is just to the right of the belly button, and the right side of this image is in fact very, very close to the hip. So it's a scan going from the belly button to almost over to the hip bone. And what you're seeing here is you see the little line right here around 8 millimeters is the fascia layer. And so here you have the superficial layer, which is about 8 millimeters and gets as thick as about 12 millimeters before you start going back towards the hip and down. Kind of a dominant feature here at around 28 millimeters is the true kind of fat muscle interface, the deep layer and muscle interface. So your deeper layer of fat is right in this pocket here. And this is important because animal studies indicate that this really deep layer of fat is metabolically active. It regulates insulin and as such is probably ultimately a better indicator of health risk than just the total fat layer. So the ultrasound and high-resolution X-ray are one of the few techniques that actually see that. And so we're very interested in the future of analyzing this and looking at the structure in more detail. I hope this short introduction to ultrasound answers some of the questions that you might have. Well, that brings us to an end of our short introduction to the technology and the science of the BodyMetrix ultrasound system. Thank you.